Hello everyone, welcome to day 18 of Leetcode-1379. Today we have question number 1192, critical connection in a network. In this question they have given us n servers, numbers from 0 to n-1, connected by undirected server to server connection, forming a network where connection I, A and B represent a connection between the server A and B. Any server can reach other server directly or indirectly through the network. A critical connection is a connection that, if removed, will make some servers unable to reach some other servers. Written all the critical connection in the network in any order. In example 1, in this graph, edge 1 and 3 is the critical connection, because if we remove the edge 1 and 3, then this whole graph will divide into two components. So that's why 1 and 3 is the edge which is connecting the graph 1, 0, 2 and 3 together. So this is the critical connection in this graph, and that is what they have written as an output. Let's understand this question more betterly using these examples. In example 1, if they asked us to find the critical connection is something like, if we remove that edge, the graph should be divided into two components, or that should be the only edge connecting the graph, so that it could not become the bridge in the graph. So if we think like edge 1 and 4 is the critical connection, if we remove it, can graph divided into two component? No, we can reach to 1 using 2 also. So this is not the critical connection. Still the graph is connected, still all the nodes are connected. Okay, so let's see now 4 and 3. Is this a critical connection? No, this is not a critical connection, because if we remove 4 and 3 also, then also 4, 1, 2 and 3 are connected. So this is not the critical connection. This is not the edge this is not the edge. If we remove it, it is not dividing the graph into many components or the two components. 2 is 2 and 3 is the edge between 2 and 3. Is this a critical connection? No, this is also not a critical connection. Similarly, 1 and 2 is also not a critical connection. So basically, if the graph is cyclic, then the critical connection will not get any critical connection. But if the graph is not cyclic, in this example, if we remove the edge between 1 and 2, this whole graph will divide it into two components, one which have a single node 1 and the other which have the node 2, 3 and 4. So this divide the graph in the two components. Similarly, instead of removing this, if we remove the edge between 2 and 3, again this graph will be divided into two components. One is of 1, 2 and other is of 3, 4. And similarly, if we remove the 3 and 4, again the graph will be divided into two components, 1, 2 and 3 and then 4. So that's why all these three edges, that is this one is the critical connection that we will return as an output. But for example, if it has one more edge, for example say 5 over here, then for the critical connection, then this will not be a critical connection, because if we remove this also, we have 1, 5 and 2. This is forming a cycle. So this like any of these nodes cannot be a critical connection. But 2 and 3 can be a critical connection, because once it is removed, graph will be divided into two components, that is 1, 2 and 5 and 3 and 4. 3 and 4 is a critical connection, this edge, because if we remove this edge, then 1, 5, 2, 3 will be one component and the 4 will be another component of the graph. So 3 and 4 can also be the critical connection. This we have to written as an output in this example. The optimal way of finding is this, using a Tarzan's algorithm, where we have to keep in mind two things. First thing is like we'll do the Dfs Traversal, and the other important thing out of which first one is we will make a discovery array, like at what number is this node discovered, and second will be what is the lowest possible node to reach that particular node. What is the lowest possible ID to reach that particular node? This you will get it when I'll just okay. And one we will have this ID integer, that will be 0. So first thing what we will do is, while we are doing the Dfs traversal from the node 0, we will assign it its ID is 0, so its discovery time is also 0, and the lowest node like the lowest node from which we can reach to this node is this node itself. So this is also 0. So when we are going with 1, the discovery at what time it is discovered, now id will become 1. So this is discovered at time 1, and the lowest possible node to reach itself for now it is 1. And then if we will go to 2, at what time it is discovered 2, and the lowest possible node to reach 2 is 2 itself. But now when again we will traverse DFS, so this will go to this, 2 will go to this node, but now the lowest possible time to reach this node is 2, and lowest possible time to reach this node is 0. So out of which is the minimum? 0 is the minimum. So we will assign the lowest possible time to this node as 0. So this node can be reached 0 time. That means there is no critical connection between these two nodes. If we remove this node also, like 0 and 2, there will be other ways to reach this node, that is 0, like using the node 1 in the middle, that is 0, 1 and 2. Okay, and then if we traverse back again, we will find that 1 and 0, which is the minimum way to reach it, like we can reach 0 is the minimum, so we will assign this as 0. And then we will traverse as we are traversing in a DFS way. So now we will move to this node, that is 3, and now again its ID will be 3, and the lowest time we can reach this node is 3 itself, because we will check whether to choose the low time or the discovery time is when we are moving back from the DFS, when we are coming back. Now we are going, now we are moving in the DFS fashion, so we will just assign the ID, like the discovery time and the load time based on the ID. But when we are coming back from it, that time we will compare it with its neighbor's load time and its load time. We are moving to 4, discovery time is also 4 and the load time is also 4. We are moving to 5, discovery time is also 5 and the load time is also 5. But when 5 is going to 3, then we will check whether the load time this is minimum or this is minimum. Obviously 3 is minimum, so that is there is not a critical connection between them. We can also reach 5 using 3, 4 and 5, and it will not divide this graph, especially this one 3, 5, 4, in the 2 component. So this means that. Similarly, when we are moving back, 3 or 4, which one is the minimum? 3 is the minimum. So similarly, even the edge 5 and 4 is also not a critical connection, because we can reach 4 using 5, 3, 4. This we can reach in this way. When, like, there is the point, whenever there is the cycle, you will not get any critical connection, so it will have the lowest value as 3. Similarly, this will backtrack again, and over here now we will see which is the lowest. Is the 3 lowest? Because it like the DFS went from here, and now it's coming back, so it will compare whether this 3 is lower or the 0 is lower. But this time when we are coming back, we will check is this lower or this lower. So this time now we will check whether 3 is minimum or 0 is minimum. See, in this case, this is lower than this, so this 1 and 3 edge will be our critical connection, and that is what we will return as an output. Because if we remove 1 and 3, it will divide the graph in 2 components. One will be of 0, 1 and 2, other will be of 3, 4 and 5, and this is what we are going to return as an output. Let's take one more example. If the graph would be somewhat like this: 1, 2, 3, and if here we would have 4, then what it would have done? First thing is, it will assign the ID 0, 0, then it will move to 2, it will assign the id 1 comma 1, then it will move to 3, it will assign the id 2 comma 2, and then it will backtrack, like it will see which is the minimum, out of which 0 is the minimum. So we will update this 0 so that this is not the critical, this indicate that this is not the critical node. Then it will backtrack again from which it came, that is it came from 2, then again it will check 0 or 1 which is the minimum, 0 is the minimum, so here it will become 0, then it will go back to 1, and then again it will check for, like now it will go to, it is going, so it will be like discovery time also 4 and the load time is also 4, but when it is backtracking it will check 0 or 4, out of which is this minimum, like is the value 4 less than 0? No, value is not 4, sorry, the value 4 is not less than 0, so 1 and 4 is a critical edge, so we will return this as an output. So let's code this question, and time complexity will be similarly of the DFS, that is big O of v plus e. This is because we are just doing the Dfs traversal and nothing extra we are doing. So the code is what the things we need. First thing is, like they have given us the connections and the total nodes. So first we need to create a adjacency list, that is we have to build the graph. And the other thing what we need to return this, so we need result, or we can call them critical connection. And the other thing is what we need an integer array which will have its discovery time, and we will need a low array which will have the lowest possible node from which it can be, that particular node can be reached. And then we will have the id which we will give. Now let's initialize it over here. Graph is equals to new array list. What will be its size? Its size will be of the node. And then critical connection is equals to new array list. Discovery time will be, this will be of low is also of n, and the id we will initialize with 0. First thing is what we will do. First thing is we will build a graph. So we will call the helper method which will help us to create the graph. And after creating the graph, what we will do, we will create a boolean array of visited which will make sure which of these nodes are visited and which are not. So new boolean n. And then the other thing is, then we will have the Dfs traversal. We will write some code over here. We'll pass some parameter, and then we will return the critical connection. So first thing is we have to build the graph. So private void, what it will take, it will take this as an input, and then we will have the for loop, integer I equals to 0, I is less than graph dot length I plus plus, and graph I is equals to new, like every node should have its own array list, and then it is assigned. Then what we will do, for list of integer in connections, we will create integer a, and connection dot get, what we will get, the 0, what is present at 0, and we will have the integer b which will have, from array we will get what is at 1. I mean 0 we will get this node, and at 1 we will get this node. and then as it is the undirected graph, so that means in A we will add node B, and from B we will make a we will make an edge to node A, and this is where our graph is built. Okay, and then we have to do the Dfs traversal. First thing is we will pass the visited array. Parent node will be 0 and current node will be 0 and the parent will be -1. Now we have to write the code to write the Dfs function. So private void Dfs, and what are the parameters we are passing? First thing is we are giving it the boolean array of visited. So next thing we are providing is the current node, and then the last parameter is the parent node. For node 0 it's -1 because it's a starting node, we are starting from there. First thing what we'll do is we'll enter this. First we'll mark this current node as visited, so its boolean array will mark it as true, and then the discovery, this node we have discovered, so it's for now it's low, and the discovery ID will be same, and then we will increase the ID, and then what we will do, we will go for its neighbor integer in graph of current node. First we will check whether its neighbor is visited or not. If it's visited, then we'll write some code. If it's not visited, then we'll write some code. So if it is visited, first we don't have to move. In order to avoid the infinite loop condition, we will check where a neighbor is equals to parent node, then we will just continue. I mean when there is just 2 nodes given, this condition of for that case, and then okay, this condition of for that case, and after that we will check this. First we will check for the 2 node condition, and then we will come here, and then we will check whether the neighbor is visited or not. If the neighbor is not visited, then we will call Dfs, and visited array will be same. Now our current node will be our parent node for the neighbor, and this parameter will be our neighbor, because now our current node will be neighbor and our parent node will be current node. Okay, so this is our neg. Okay, done. After this we'll call the Dfs, and then we will check when we are coming back from the df, like when we are backtracking. So when we check our low of the current node, mat.min will keep the value, compare between the low of the current node and the low of its neighbor, which will from both which will have the minimum value, just assign it to the current node, and then if discovery time of the current node is less than the load time of the neighbor, that this is the point we can say where we got the critical connection. Then we will add in the critical connection, that is arrays as list, the current node and the neighbor. This so far so good. And the else condition, if the neighbor is also already visited, then we will just check the current node low and math dot min of low of the current node. Now this time we will compare with the discovery time of the neighbor. And we are done. Let's run it. Let's submit it. Okay, is my network slow? Okay, so we are done. Thank you.